looking at problem number 7, which is dealing with 4 flips of a coin. Now, the ideal result for 4 flips of a coin. Okay, if we count the number of heads, well, the number of heads can be 0, 1, 2, 3, or 4. There's one way to get 0 heads. That is to get tails, 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 tails. There are 4 ways to get 1 head. Okay, head, tail, 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 head, tail, 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 head, tail, 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 head. Okay, we could list those, and we did in class, and everybody should be familiar with that. So then if we continue listing, it turns out there are 6 ways to get 2 heads, 4 ways to get 3, 1 way to get 4 heads. Now, as it's going to turn out, it will calculate a mean and a standard deviation over here. If you calculate the mean and standard deviation of this distribution, the mean is 2, which means that you would average 2 heads. If you flip 4 coins a large number of times, you would tend to average 2 heads per trial, with a standard deviation of 1.03. Now, we did that in class. That's just kind of a review of the results that we got for 4 flips. Now, problem 7 gave you a whole page, actually 2 pages. You probably can't read this. I don't know how the light works with this camera. I know it doesn't work well, but I'm not sure what the details are. Okay, well, you had a list of 64, I think, flips of the coin. I counted up how many times you got 0 heads, 1, 2, 3, 4. Now, the results for head or tail on the result for each flip was obtained by just generating a random number, not randomly between 0 and 1, and then assigning heads if the number was greater than 0.5, tails less than 0.5. Okay, in that process, we can tally the results. If you go down through the heads and tails, we got 0 heads once. We got 1 head 14 times, 2 heads 27 times, 3 heads 19 times, 4 heads 2 times. That only totals up to 63. It means I missed 1 somewhere. Okay, so there's kind of a check of my accuracy in tallying these. I was pretty accurate, and the result that we're going to get is close to the result that you would have gotten had you counted them correctly. We had one case where there were no heads. So the X value for no heads is 0. The frequency is 1, happened 1 time. Well, that totals up. If we total for each X value, the total for 0, for the outcome 0, the total number of heads we got is 0. Okay. Now for 1 head, that occurred 14 times. So the total for that X value is 14. There were a total of 14 heads that occurred when you had outcomes with just 1 head. Okay, 2 heads occurred 27 times, which gives us a total of 54 heads for the outcome 2. 3 heads occurred 19 times, total of 57 for the outcome 3. 4 heads occurred twice, total of 8 heads for the outcome 4 heads. Now, the mean number of heads that we got, well, we simply add these. We get 133. You can check the arithmetic. And we divide that by 63, and we get the mean, which is 2.11. Now, what's the deviation of each of these outcomes from the mean? Okay, the mean number of heads was 2.11. Notice that that compares pretty well with the expected mean of 2, with the ideal mean of 2. It's pretty close to 2, but by the random process, it came out a little higher. Okay, well, we have a mean of 2.11, so when we got 0 heads, that deviated from the mean by 2.11. When we got 1 head, that deviated from the mean, which is 2.11 heads, by 1.11. And 2 heads deviated from this mean by 0.11. 3 heads deviated from the mean by 0.89. And we just subtract the 2.11 from 3 to get that. And the 4 deviated by 1.89. Now, in calculating a standard deviation, which is what we're leading to, standard deviation is defined as what? It's the square root of the mean, quotes around the mean, of squared deviations. Remember, the quotes around the mean says if you have fewer than 30 outcomes total, you got to divide by one less when you're calculating this mean. We have 63, and we should actually have 64. So we're going to divide by that number when we calculate the mean of the squared deviation. Okay, well, before we can do that, we've got deviations. We need squared deviations, so we square these numbers. Then we've got to count each squared deviation, the number of times it occurs. Okay, this deviation of 4.46 occurred once. And of course that arose when we had x value 0, so the deviation was 2.11, square deviation 4.46. We multiply the one time that occurred by the square deviation, and we get the total square deviation for that x value, which is 4.46. We have a deviation of 1.24 when we get one head. Well, that occurs 14 times, so we're going to multiply 14 by 1.24 and get a total of 17.3 for the total square deviations corresponding to an outcome of one head, which occurred 14 times. Okay, and for two heads, the deviation was small, just 0.11, the square deviation 0.12, but we're going to multiply that by the 27 times that outcome occurred to get this, which will have to be added in when we calculate the total squared deviation. And then the 0.79 square deviation for an outcome of 3 occurred 19 times. Multiplying 19 by that, we get 15. And for standard deviation 4 occurred twice. Square deviation is 3.57. If we double 3.57, we get 7.1. Actually, if we double 3.57, that gives us 7.14. Yeah, that runs up to 7.1. I don't know what I was thinking. Okay, so anyhow, these are the numbers that we get, and we add these up, we get about 44. That's the total of our squared deviations. Why would we total our squared deviations? Why did we even calculate our squared deviations? Because the standard deviation involves squared deviations, and it involves taking the mean of the squared deviation. So we've got to add all of our squared deviations up, and then to get the mean of the squared deviations, we'll divide by the 63 outcomes that we observed. There were 63 lines in that table, 63 deviations, 63 squared deviations, and here's the numbers that we add to get the total. So we added those, we divide by 0.63, get something very close to 0.7. Standard deviation is the square root of the mean of the squared deviation, so we take the square root of 0.7 and we get about 0.84. How does this compare to our ideal? Well, 2 is pretty darn close to 2.11. The means are pretty close. Standard deviation 1.03. This standard deviation was about 20% lower than that one, but it still compares reasonably well. Now, if we were to draw normal curves, you weren't asked to do this, but just a little extra. If we were asked to draw the ideal normal curve and the normal curve that we would have concluded from these coin flips, from these random numbers, modeling the coin flips, we'd have just a slight difference in the curves. So I'm going to sketch those real quickly. To start the sketch, I draw two horizontal lines, and I put the number 2 on this line, the number 2.11 on this line. I've got kind of a dotted line here showing how that 2.11 is a little bit to the right of 2. Then the standard deviation. Okay, well, the mean here is 2. The mean plus 1 standard deviation is going to be 3.03. The mean plus 2 standard deviations will be 4.06. Now you remember how to draw a normal curve. This mean point, 1 standard deviation, 2 standard deviations. Well, we'll get to that in a minute. I'm going to write a few more things on here. Okay, I've labeled 0.97, which is 1.03 below 2, and negative 0.06, which is 1.03 below that. So I've got the numbers up here, which are 1 and 2 standard deviations below the mean. I've indicated some z's down here, negative 2, negative 1, 0, 1, 2. I believe everybody should know what that means. It's just the z values corresponding on this graph to these numbers, and down here corresponding to these numbers. Now, these numbers are obtained by starting at 2.11, adding 0.84 to get 2.95, adding 0.84 again to get 3.79, then subtracting 0.84, and then subtracting it once more to get the numbers that correspond to the z values on the numbers from the simulation, from the simulated values. Now we remember how to sketch a normal curve. We start with a line in the middle, and we try to get this line and the line up here to correspond to the mean. Now, we want the area under both curves to be the same. Since this curve spans slightly wider values than this, we want the central value to be a little higher. I probably exaggerated how much higher it needs to be, and also didn't draw it very straight, so we're not going to get a great picture here. But now we draw the number out here that's 60% as high as that, and we'll represent that here. Number that's between 1/7 and 1/8 that height, and we do the same over here. And I'm going to do the same down here, but I'll do it off camera just to save you a little time. So here are my two pictures. Now it appears that this one has greater area than this one because I did something ridiculous a minute ago. I said this one is wider, so to get the same area, this has to be higher. That was really pretty stupid, if you don't mind my using that in reference to my own action. So I kind of screwed that up. I tried to make this one higher, but I didn't make it higher enough, and so it came out a little smaller than it should. I should have compensated this, made this one somewhat lower, and made this one, well, let's say the size it is. I'm going to actually fix that. Okay, looks like the paint is almost dry. So now this one isn't as high as this one, but it's wider. This one is a little higher, but not quite as wide, and I'm not even sure that's even still true. Yeah, it is. It is. Okay. So they should have the same, they should represent the same, they represent the same area. The area is 100% of a distribution should lie under the curve, so the area of each curve is 100%, but they should look kind of comparable when we draw them this way. Okay, so now we have a good picture of how this random this randomly generated simulation of flipping 4 coins compared with the ideal. We don't expect a random event like this to perfectly mimic the ideal. We're going to get a few more of one, a few less of another. On 64 flips, we would actually expect to get 30. No, actually, let's see, on 64 flips, we would expect to get 24 occurrences of 2, and we would expect to get 16 occurrences of 1 or 3. Well, we're pretty close, but not exactly. And we would expect to get 2 zeros and 2 4s, and we came pretty close to that. So this came out about the way we would kind of expect it to, but it didn't come out exactly. So the standard deviation and the mean didn't come out exactly the same either. So the numbers show pretty good agreement. The resulting pictures show pretty good agreement. But if we had many, many more flips, we would likely get much better agreement. And should the number of flips increase without bound, we would expect the agreement to approach perfection.